Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline and want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today, that's Linode, and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. We've all been asked to help with an ad hoc request for data by the sales and marketing team. Then it becomes a critical report that they need updated every week or every day. Then what do? Send a CSV via email? Write some Python scripts to automate it? But what about incremental sync, API quotas, error handling, and all of the other details that eat up your time? Today, there is a better way. With Census, just write SQL or plug in your DBT models and start syncing your cloud warehouse to SaaS applications like Salesforce, Marketo, HubSpot, and many more. Go to dataengineeringpodcast.com/census today to get a free 14-day trial. Your host is Tobias Macy, and today I'm interviewing Andy Pavlo about OtterTune, a system to continuously monitor and improve database performance via machine learning. So, Andy, can you start by introducing yourself?
My name is Andy. I am the co-founder and CEO of the OtterTune startup. I'm also an associate professor in the computer science department at Carnegie Mellon University.
And do you remember how you first got involved in the area of data management?
So my PhD is from Brown University in databases. I didn't plan on doing a PhD in databases at the very beginning. I was originally interested in distributed systems, but with databases, it sort of turned out to be this thing where I seemed to understand it better than other people. What sort of was challenging for other people and like working with databases and using databases sort of came naturally to me. So this is sort of how I ended up in this space. And then when I started at Brown, my advisors were Stan Zadanek and Mike Stonebreaker, and they were building a brand new database system from scratch called HStore, and I was recruited to work on that project. And so I've been building database systems since then.
Yeah, must have been a privilege to be able to learn about databases under the tutelage of Mike Stonebreaker, because he's kind of legendary in the space.
Yeah, I did a pre-doc at the University of Wisconsin, before I started my PhD when I was out there, and I just remember this was the first time I started hearing the name Mike Stonebreaker, and he just came up in various conversations about all the great things Mike did and how he was this amazing researcher. And then when I finally got to meet him, a bit of surprise because he's very quiet. He's very tall. I think he's 6'6" is the official measurement. He was a larger than life figure, and I'm very grateful for the time I got to spend with him.
And so you've been working in databases for a while now, and OtterTune is something that is aiming to help with tuning and maintenance of databases. I'm wondering if you can just start by giving a bit of a description about what the OtterTune project is and some of the story behind how it got started and the goals that you have for it.
So OtterTune is an automated database tuning service that targets database configuration knobs. So by knob, I mean a control parameter or configuration parameter that the database system exposes to you as an administrator, as a user, to allow you to tweak the behavior of the system. And the reason why these knobs exist is because when the database developer was building the database system, at some point they had to make a decision about allocate memory for a hash table or something about the feature they were building. And then rather than using a pound define that was meant to be for all potential users, they instead kick it out as a configuration knob because they assume that someone else is going to come along who knows exactly how the application wants to use the database system and will be in a better position to set it correctly. These knobs cover things like buffer pool sizes, caching policies, log file sizes, various aspects of the database system's runtime behavior. And so if you can set these knobs correctly for how the application is going to be using the database, like what kind of queries it's going to run, and what the environment looks like, what the hardware looks like, then you enable the database system to run more efficiently to achieve either better performance or reduce the cost of the deployment. So I got down this path of, the project originally started my first year in 2013 when I started at Carnegie Mellon University. And I was looking at how could we use machine learning to automatically improve the performance of a database system. And so there had been a ton of work going back to the 1970s automatic database design for picking indexes and partitioning keys. I had done some of that work when I was in graduate school. But then I felt that there really wasn't a lot of stuff looking at how to automatically configure knobs. There was some work done in the 2000s. Commercial systems had these tools that were rule-based that could set these things, but no one sort of looked at, can you sort of holistically look at the database system through these knobs and tune them correctly, and then be able to reuse the training data you've collected from one tuning session for one database and then apply it to another database. So all the existing tools that existed that were doing some amount of machine learning were always learning everything from scratch. So we thought, like, okay, what can we do to expedite the process and learn from one database and apply it to another database? And in particular, I also was interested in how far could we get without having to get access to real-world queries and data sets. So the way OtterTune works is that we only use the metrics that the database system generates and exposes to you. We don't need to see any user data or query traces, which was a big problem when I was in grad school to try to get access to these things. So we looked at a way to not have to, ask for this kind of data from people outside of the university.
And I know that, I think it was a few years ago now, there was a research project that was building custom indexes based on machine learning, based on the usage of the data that gave better performance above things like a generic B tree or a hash index. But that obviously requires access to the data that's in the table. And so I can see where, that's definitely something that's challenging and would have to live within the database and not be able to have any external access to it. And so I'm wondering what you've seen as far as the potential performance capabilities of changing these configuration parameters based on the actual database workload as compared to something like generating customized indexes based on the data that's in the tables.
Yes, so the learned indexes, that's a separate topic. We can come back to that. It's tough to compare, right? There are two different approaches to sort of a white box approach. With OtterTune, it's a black box approach. So again, we don't control the internals of the database system. We don't require the user to install any kind of special extensions. It only looks at the database using the APIs that the system already exposes and the information that it already exposes. And so the benefit you can get from automated tuning with something like OtterTune will obviously depend on many factors, as in all cases in databases. Depends on what the queries are, how big the database is, depends on whether you've already tuned it or not. We see people still using the default configuration that Amazon gives you on RDS, which Amazon has tuned it a little bit, but it's still not as good as what you could achieve if you tailor it explicitly for the application. So it's tough to say, like, oh, OtterTune is going to give everyone a 2x benefit. If you've already tuned some things a little bit, then the benefit we can provide is potentially lower. Now, I will say that we've done real-world deployments of OtterTune where we have compared it against configurations that have been tuned by human experts, and OtterTune can still, through the algorithms, can still find some room for improvement. So we've been pretty happy with that outcome of, like, even after a human expert has gone at it, we can do a little bit better.
And another project that you've been involved with in your time at CMU is the noise page database, which is an entire engine that's built around the idea of being maintenance free and automatically tuning itself. And I'm wondering if you can provide some details as to any lessons that you've learned from your work at Noise Page that have been applicable at OtterTune and vice versa, and any sort of relationship that might exist between the two projects.
So my research is divided into two tracks. There's the OtterTune project, which was taking a black box approach to automatically managing database systems. And then the Noise Page is a white box approach where if you're designing the database system from scratch with the assumption that it will be entirely controlled by machine learning algorithms. So with Noise Page, we make certain decisions as we build the system that are not going to potentially achieve the best performance, but it makes it easier to control and observe its behavior while it's running, which is what you need to happen if you want to be completely autonomous. So with Noise Page, we've been dubbing this as a self-driving database system, and I realize Oracle uses that kind of language in their marketing. I disagree with their characterization of what they're doing. So in Noise Page, with what I'm defining as a self-driving system is one that can forecast the workload in the future, proactively make changes to prepare for it, and then observe those changes and learn from them. Things like OtterTune and other sort of autonomous tools that are out there, they only solve half the problem. They only tell you what to change to make things better, but they don't tell you how and when to apply those changes. So with noise page, we want to complete the circle and have the system automatically figure out, okay, these are the changes I need to make, picking indexes, tuning knobs, changing hardware configurations, and then apply those changes, observe what happens when you make the changes, and then repeat the process over again and learn from them. So the lessons that we've learned from our research have mostly gone from the OtterTune side to the noise page side. So I've seen the struggles that we've had in trying to get OtterTune to tune Oracle and Postgres and MySQL and other things. And we then go and say, okay, well, now when we build our system, let's not make those same mistakes. The clearest example would be having to restart for some knobs to take effect. So in every single database system that's out there, there are some knobs where you can make the change, but the data system actually doesn't apply them until you restart the system and come back online. The open source guys have a bunch of these knobs that are like this. The commercial guys have them as well. There's fewer of them, but nobody is immune to this issue. So in the case of noise page, we've tried to build the system so that any change like that doesn't require us to have to restart the system. Because if you have to restart the system, and now you need to know whether you're allowed to even restart, because that's an external cost that the algorithms can't easily reason about. Like, I don't know whether at 1 o'clock in the afternoon, is it okay for me to take your database online for an hour? Probably not. I don't know what the implications of that are. So in OtterTune, you have to manually tell us when you're allowed to restart. In the case of noise page, we said, let's avoid that problem entirely, and let's build the systems that we don't have to restart at all.
Going back to the knobs that are available to operators of the databases, I'm wondering if you can just talk through some of the kinds of challenges that database administrators and operators and end users of the system run into when they're trying to figure out how to optimize the system, tune it for their workload, or just get some, performance improvements if they see that they're starting to hit some limitations with the way that they're using the platform, and just some of the sort of sources of that complexity and confusion that arise.
So the way people can tune database systems now, tune the knobs now, there's essentially 4 ways to do this. You can try to do it yourself, and it usually falls into the DevOps role. And this is where you have somebody who maybe knows a little bit about how a data system works, but maybe doesn't know entirely all the internals. And what they usually end up doing is just Googling, how to tune MySQL, how to tune Postgres. And there's a bunch of these blog articles written by some of the database consulting companies and the vendors that will give you some rough guidelines on maybe 5 knobs you could try to tune. And they tell you, calculate the formula to how to tune them. Like, how much RAM do you have, how much CPU you have. In our experiments, we actually found some of these recommendations of these blog articles for Postgres and MySQL were actually incorrect. It varies widely in the application. If you have a little bit more money and have time, you can hire a DBA to come in and try to tune these things. And these are people that have experience in tuning. But typically, they're only going to maybe tune 10 to maybe 12 knobs, if that. And we've found that for things like Postgres and MySQL, there could be a couple dozen knobs that actually could affect performance. And there's going to be implicit dependencies between these knobs that are not readily understood or discernible by humans, where you maybe tune one knob and that changes how you want to tune another knob. It changes the behavior of that other knob. And so it's very difficult for people to reason about these things. The next approach would be these tuning scripts that are available, where you punch in some basic information like how many cores you have, how much RAM you have, maybe what the disk and what the workload looks like. And then there's these hard-coded formulas in these programs where they just spit out some recommendations for some knobs. So all the major database vendors have their own things. And then for Postgres and MySQL, there's open source tuning scripts that are available. And again, these are like the lowest common denominator. They're not going to be explicitly for your application. It's going to be sort of general purpose. And we have found that in our own experiments, we can beat those things pretty easily. So the challenge is a combination of not knowing what to tune, not knowing how to tune them, not understanding that if you tune one knob, that could affect other behaviors of other knobs. And then, probably more importantly above all of this, is just a matter of time. Like, it takes time to try these knobs out and see whether they're actually, making a difference or not. And then you have to manually keep track over time, like, okay, what knobs did I change? Did that help me or not? And, with DBAs and developers and DevOps, people just don't have time to do these things. They have all this other stuff they have to do at their jobs. And database tuning is almost always relegated to something like, I'll get to it when I can. And unless a performance issue comes up, but then by then it might be too late, and you still have to do this manual process of trying to figure things out. So OtterTune takes a lot of this complexity and takes a lot of this hardship away, because we can automate as much as possible this process of figuring out how to tune your database system. And it can reason about the complexity of all these different knobs in a way that humans just aren't able to do.
Looking at some of the configuration options for the different databases, there are, potentially dozens, if not hundreds, of configuration parameters. And I'm wondering what you have seen as some of the contributing factors to adding in all of these different options that lead to this potential complexity and all these different sort of implicit dependencies in terms of the impact that setting, a handful of different values together will have, and not being able to sort of clearly describe what the relationships are, and just sort of the evolutionary and sort of incidental complexity that comes out of that.
Database systems are complex pieces of software. And so it's not surprising that they have a lot of knobs that you can tune because a lot of features in them. And when you look at very popular database systems, Oracle, Postgres, MySQL, SQL Server, all these systems over time have added new features and it's gotten even more complex. So it's not surprising that the number of knobs that they expose has been increasing. So my PhD student, part of her research, she did a survey where she looked at the last 20-year release history of Postgres and MySQL. And then for every release, she just counted the number of knobs that they listed in their documentation. Over a 20-year period, MySQL increased by 7x and Postgres increased by 5x of the number of knobs that they have. So not all of these knobs are going to tune and affect performance. They're going to be things like file paths and port numbers or things that you're not going to want machine learning algorithms to set for you. But there's still enough of them that can affect performance. And so figuring out which ones actually you want to tune is challenging. Yeah, I say also too, so depending on the workload, some knobs actually don't do anything. If you're not inserting any data, it's just read-only queries, then the knobs related to inserts probably, potentially won't make a difference. So just knowing what you should be tuning is another challenge as well. So I think these systems are very complex. They're very popular. People are adding new things up to them all the time. So that's why the number of knobs they've exposed has grown so much. Now, with things like commercial systems like Oracle, it's even more difficult because there are some hidden knobs that you're not supposed to tune that can affect performance. And in Oracle, they start with an underscore, and the super secret ones that you're never supposed to touch are double underscore. You can tweak the single underscore ones. You're not supposed to in some cases, but you could. And so that just makes it even harder to figure out what's going on because now there's all this other class of configuration knobs that I could be touching, and I don't know whether I should be or not. So the problem is certainly grown, and it's not something that's going to be easily solved in the future. The database vendors are not going to remove these knobs because they're there for a reason.
With the number of parameters that are out there and the fact that not all of them are going to have an impact on performance or scalability, I'm curious what your approach has been in terms of identifying the parameters that you want to look at and building the machine learning model to be able to understand the impacts that it has, and just the overall approach that you've had to actually building out the OtterTune system for being able to learn and intelligently determine which configuration parameters to set and what values to use for them.
The first thing we do when we bring on a database system is when we want to start including knobs. So let's say there's a new release of Postgres and we want to incorporate it into OtterTune. We go through the documentation and we have to manually look at the knobs and identify whether there's a potential to tune them. If it's a host name or file path, we obviously don't touch those things. And we include those in our deny list of what we don't let OtterTune touch. But then a bit more tricky problem is for the knobs that we do think we potentially want to tune, we have to go through and determine whether if we let the algorithms tune them a certain way, could that cause an external cost? Is there an external factor that we'd have to take into consideration? So, for example, most databases, you can turn off whether you want to flush the log to disk when a transaction commits. And so, obviously, if you don't write to disk, your database runs a lot faster. So the machine learning algorithms will find that turning off disk flushes makes things go faster. But there's an external cost to that because if now you crash and you lose the last 10 milliseconds of data, the algorithms don't know how that's going to affect your company or how it's going to affect your organization. You can't measure that. That's something we don't know whether that's the right thing to do for a customer, for a database. We also prevent OtterTune from tuning those kind of things as well. So we have to manually go through the documentation, and since we know database internals, we can decipher and understand what's going on. In some cases, we've looked at the source code for Postgres and MySQL to understand what is this knob actually doing to determine whether it's safe for us to tune it or not. So that's sort of the first step to go through and figure out what should be allowed to tune and which shouldn't be tuned. You go from a couple hundred to a couple dozen, less than 100 knobs that you could potentially tune for Postgres, MySQL, and Oracle based on this.
The other interesting challenge to that, and I'm sure it just ends up turning into code spelunking, is for the cases where a parameter is maybe a string or an enum where it only accepts a certain limited number of values that you need to make sure that you get correct, or else it's just going to fail, either fail to start or just not have any effect. And I'm wondering how you handle the variability in data types, and in particular things like enums where it's this stringly typed value that has to match exactly what's in the code.
Those aren't an issue. The enums aren't an issue because those are just categorical variables in our machine learning models. So you just convert them to integers and the algorithm can deal with that. And in terms of the machine learning side, the algorithms don't know what they're actually tuning, right? It doesn't know that this knob is going to affect something in the disk and something to affect, the write-ahead log. It just knows that if I changes them a certain way for a particular database, it makes my objective function better. Like, is it improving the throughput? Is it improving the latency? So as long as we convert the options that are available to tune the knobs, either the range of values or a discrete set of values, as long as we convert them into integers that we can then build models on, it's not that difficult to add new things or incorporate, as you said, strings or enums.
Can you describe a bit about how the OtterTune system itself is actually implemented and some of the ways that you think about building the reward functions for optimizing for, whether it's cost or throughput or latency and things like that?
So the way it works is that you provide OtterTune with some basic login credentials to access the database system. If you're running on Amazon and using something like RDS, you provide us an IAM role to access the parameters, the knobs from Amazon's platform or service, and as well as a severely limited login credentials to access the database directly. So when we access the database, the only thing we need to retrieve are the runtime metrics, like the internal performance counters of the database, pages read, pages written, things like that, and then the current configuration. And then we have a driver running in Kubernetes that can connect to the database and retrieve this information. We then store the metrics and the configuration for the database in our internal repository with all the other training data we collected from all other databases. And then we have a set of Kubernetes jobs that run to train the models based on this data. We support different machine learning algorithms. We've done Gaussian process models, deep nets, and then reinforcement learning. We haven't really seen a major difference just yet in the efficacy of those algorithms, although they can have different convergence rates. That's not the main issue we're hitting right now. So then you have to specify what you want the reward function to be or what the objective function should be. Do I want to, again, maximize throughput, minimize latency? You can also provide a alternative metric that maybe isn't coming directly from the database system. So it could be like a monitoring service, an APM service, where you're keeping track of something that's outside the database system. Again, that's just another metric we can record and try to optimize for. So then, based on that, we then run a recommendation algorithm to generate new values for the knobs that we want to tune. We send them back over to the driver, who then applies it to change the database. If that new configuration requires a restart, and we're allowed to restart at the time, we'll go ahead and restart. And then we observe the effects of this. And so repeating the process, applying new configurations, observing whether it's helps us. And over time, the models will converge, and we think we have the best configuration for your workload right now. Then we can switch into this monitoring mode where we're not actively tuning, but we're making sure that the configuration you currently have is the best thing for you right now.
As you started building the project, I'm wondering what are some of the ideas or assumptions that you had about either how you would approach it or the sort of capabilities that it would have that have either been challenged or invalidated as you progressed through building the initial prototypes and into real-world systems and then started getting it into the hands of end users?
It's not so much the service itself, it's the how we would set up the environment for the database to tune it. So for the deployments we've done, there have been sort of two variations. You either make a clone of the database and capture the workload, and then you run a backup machine or a spare machine and run all your tuning experiments there. And then once you think you have the best configuration, you then apply that change to the production database. We've also done another deployment where we've run directly on the production database, but it's a read replica for backend services. And in that environment, we didn't have to capture the workload. We didn't have to make a snapshot of the database. We just run directly on the production database as it was running queries. But in that environment, since you don't have a baseline to know whether you're making things better because the workload is changing over time, we had to connect to another database as the control. It's running roughly the same workload, and then we observe whether, as we make changes, are we doing better than the control database. So those are sort of the two setups that OtterTune can work in. The challenge has been that people just don't have the ability or don't have the time to do a snapshot and capture the workload trace. Like getting something set up where you can run on backups and tune on spare machines, that's been harder than I thought it was going to be. And again, that has nothing to do with machine learning, has nothing to do with all the algorithms and the optimizations you can provide. It's just the infrastructure that people would need to tune a database and then without touching the production database. Like that part has been harder than I thought it was going to be. One of the deployments we've done has been with Oracle. Oracle has really great tools to make do workload capture and do snapshots. The open source ones for Postgres and MySQL aren't nearly as sophisticated. So that part's been challenging.
In terms of the actual design and goals of the system, I'm wondering if there have been any changes to the kind of priorities that you've had in building OtterTune or the architectural aspects of actually building and managing it.
So the one thing that surprised me the most is that we started off with supporting Postgres and MySQL RDS. But for our inbound requests, it's been Amazon Aurora has been the thing that everyone's asking for. In some ways, it doesn't surprise me because Amazon's crushing it with Aurora. But that's the one thing that I was not expecting. That like everyone has been asking us, can you optimize Aurora for both Postgres and MySQL, but more Postgres than MySQL actually. That's the one thing that surprised me the most. The other thing that surprised me too is that a large number of people are running with the default configuration from Amazon. Again, Amazon has already tuned this a little bit, but it's still not optimal. People, they either don't know they should be tuning it or they don't know how to tune it.
And in terms of actually adding support for a new database engine or a new deployment target, I'm curious what's actually involved in being able to identify all of the configuration parameters and add them into your model and be able to build in the information into the model itself to be able to make those intelligent decisions. And sort of tangential to that, I'm also curious if you actually have to have separate models for each of the different database engines, or if there is overlap enough between them that you're able to take some sort of core element of it and just have additional parameters that go into it based on which engine you're working with.
The last question first. You're not able to reuse the training data from different database systems. So I can't take any training data I collect from MySQL and reuse it on Postgres. These systems are just so different. The knobs are different. The behavior gets changed by the knobs are different. There's no easy way to map any of the data from one database and apply it to another. It's even also challenging to reuse the training data across different versions of the same database system. So, taking Postgres 9.6 data and using it on Postgres 10, 11, 12, 13. We have done some experiments on this. The challenge is that some knobs get dropped, some knobs get added, some metrics get added. The effect of knobs can also change. And so we've done some experiments on this, but we found that it was just better to train the model from scratch using the data from the same the major version of the data system. You can take Postgres 10.1 data and use it on Postgres 10.2. That seems to work, but going from 10 to 11 or MySQL 5.6 to 8, I think that's just too difficult. And then, so the other question is what does it take to bring on a new database system? As I said, the first step is just looking in the documentation, figuring out what are all the knobs that are available, understanding what they actually do, so at a high level, and determining whether this is something we actually want an automated system to tune. Because again, we don't want to cause issues for customers or for users of OtterTune where we're making the database go super, super fast because we're turning off disk writes or we're turning off the write-ahead log. All of those things are bad because when there's a crash, when bad things happen, which will happen in a database, we don't want the safeguards that the database system provides to be turned off. So once we figure out what knobs we actually want to tune and understand what are the possible range of values for those, the next step is then to figure out what is the interface that the database system exposes to you to retrieve the metrics and retrieve the configuration, and how do you make changes to the knob values. Then another big part of this is how to make the change to the database, apply the knob values, but then observe or check whether there's a problem with those configurations and the data system will refuse to start or refuse to apply them. So an obvious thing would be if I set a size of a memory pool to -1 and I restart the system, in most databases, they'll restart and throw an error and say, I can't have a -1 value for the amount of memory I want to use. And so we end up having to scrape logs and determine whether things are not restarting correctly because of something we're doing or some other issue. So there's a bunch of that kind of bespoke safety checks we have to apply for each database system. So the combination of those three things that take up most of the time. Again, notice I didn't say anything about the machine learning stuff because the algorithms don't care what database systems they're tuning. The same algorithms can be reused across the different system types. It's just the data you're feeding into them can't be shared. So from a machine learning perspective, it's not a lot of work for us to onboard a new system. It's just the infrastructure to accommodate it and make sure that we're doing things correctly and safely. That's what takes most of the time. It's sort of a combination of knowing something about databases and machine learning to make this all work, which is hard to find these days.
And it sounds like outside of the machine learning aspect where you have the algorithms, they do what they're supposed to do, you figured out what the appropriate reward functions are. But in terms of actually onboarding a new database, each time it's as if it's the first time that you're doing it because every database is just so different in terms of the parameters that they're providing.
Absolutely, yes. The knobs are different, the metrics are different. There's other aspects of them that were unexpected too, like sometimes there's global metrics, like here's the amount of data I read for all my tables in my database, for all my indexes. And sometimes there are sort of database object level metrics, like here's all the data I've read and written for this single table. Like every database is different, and it just takes time to sort of unify what they're generating to produce and feed into our algorithms.
And I'm wondering, as you've gone through these exercises with these different databases, if that's given you any thoughts on what the sort of core logical aspects of database engines coalesce to, and if there are any learnings from that could be used to improve the overall sort of structure or approach of database engine design. I mean, obviously, you're not going to retrofit some of these existing systems, but as you work on new research projects or work with new database engines, if that has given you any thoughts on how to make these more sort of uniform in the core elements while still being customizable enough and special cased enough to be useful for the domain that they're targeting.
What I was saying before, it's what are some of the things we learned from OtterTune that we've then used to guide some of our research directions in the noise page project. I mentioned the no restart one. That's a big issue. It's not so much like the core engine, like is it a column store, is it a row store, is it vectorized, or is it doing query compilation? There are some nuances to that. At the high level, it's observability and control is the main thing if you want the database system to be controlled by an autonomous agent, right? So for example, like in MySQL, the knobs that you can set that don't require a restart, not all of them get changed instantaneously. MySQL will apply the change incrementally, but it doesn't alert you. There's no programmatic way to know from the outside, other than maybe scraping the bug log, to know when that change has been fully applied. And the reason why that matters, if you're thinking big picture of like, can I have a system that's completely autonomous? I need to know whether I'm seeing a degradation in performance or a change in my objective function while the change is being applied because the workload has changed, the hardware has changed, or like some other aspect of the environment has changed, or is it because I'm making that change? Think of it like if I'm going to build an index, I have to take away some CPU cores and use some disk while I'm building that index, and therefore I'm going to see a reduction in performance. So I need to know from my autonomous planning agents whether that reduction in performance is because of some action I applied or because the workload has changed, the hardware has changed. So I think that's the thing that we found that matters, is actually going to matter the most. It doesn't matter whether it's Postgres style MVCC or Oracle or MySQL style MVCC. From the perspective of having used machine learning algorithms to control these things, that stuff doesn't matter.
RudderStack's smart customer data pipeline is warehouse first. It builds your customer data warehouse and your identity graph on your data warehouse with support for Snowflake, Google BigQuery, Amazon Redshift, and more. Their SDKs and plugins make event streaming easy, and their integrations with cloud applications like Salesforce and Zendesk help you go beyond event streaming. With RudderStack, you can use all of your customer data to answer more difficult questions and send those insights to your whole customer data stack. Sign up for free at dataengineeringpodcast.com/rudder today. In terms of actually setting the parameters, you mentioned that for RDS environments, at least, you get IAM access to the parameters for the specific engine. So you can obviously set those programmatically, but I'm curious what your approach has been for being able to handle things like the database engine is running on, a physical box or an EC2 instance, and you actually have to make a change to the file on disk to set this parameter, or what the breakdown is of values that can be tuned from within the database engine by issuing a SQL statement to modify the the runtime configuration versus having to make these changes on disk, and just how you approach the continuum of how to actually make the change.
Every environment is different. Every database system is different. So you're absolutely right. So sometimes you need SSH access to log into the machine where the database is running and make changes to the configuration file on disk. You certainly have to do that in MySQL 5.7. But then in MySQL version 8, you now have the ability to make changes and persist them entirely through SQL commands. So you don't need access to the file system. In other environments, sometimes they're using like Puppet scripts to install configurations. So we have to go somehow modify that config file so that Puppet applies the change. Every database system, every environment is different. What's the nice thing about RDS, and I suspect Azure and GCP are the same way, they provide a standard interface that we can use to make these changes. If you're running on-prem or you're running self-managed inside of EC2, everybody's doing something different. There hasn't been an easy way to just unify all these things.
The database engines that we've been talking about so far and that you've targeted for your current system that you're offering with OtterTune are all transactional systems primarily. And I'm wondering what your thoughts are on the utility of something like OtterTune for analytical databases or data warehouse engines.
On the research side, we have done experiments of tuning analytical databases. I think we tuned VectorWise, or Actinian Vector now it's called. We looked at tuning Greenplum, but there was a bug in it in Greenplum's issue that was not something OtterTune could control. So again, the algorithms don't care that it's a transactional workload or operational workload versus analytical. If there are knobs that can be changed that will affect performance, OtterTune can learn that. We can apply those changes. So we have done tuning for analytics in the past. For MySQL and Postgres, most people are running these on operational workloads. They do have some analytical stuff that they do want to run on MySQL and Postgres. You do have to be careful about like what the objective function is. If you have a mixed workload of like, if your P99 latency of the analytical queries is like through the roof, then how do you know you're actually making the shorter queries run faster? There's some extra work we have to do on our side to handle to sort of two objective functions at the same time. But again, the algorithms at a high level are still the same. And there's nothing preventing OtterTune tuning analytical workloads. Nobody's really asked us to do this too much yet. Now, some systems or some databases that are like a database as a service, like Snowflake, they don't expose any knobs to you as the end user. So there isn't actually anything that OtterTune can tune through like a SQL interface. We'd have to be on the inside and be able to tune things for them, which we think we could do. We just haven't done that yet.
As you have been working with these database engines and figuring out how to optimize their performance and latency and twiddle all the different knobs, I'm wondering what are some of the most interesting or esoteric configuration options that you've come across, or something that just made you really either scratch your head or facepalm that, why is this even available as a configuration parameter?
The really bizarre esoteric things like the hidden knobs in Oracle, we don't want to touch. OtterTune currently doesn't tune those things just because we're trying to be very conservative about what we're actually tuning. Because again, it's the database. People are very paranoid about losing data, rightfully so. So we don't want OtterTune to cause problems. The thing that we haven't come across any knobs that I would say that are too esoteric or bizarre. They're like, why would you ever want to tune this? At least I can't think of any offhand. I mean, one of the most surprising things has been, as I mentioned, like things that a bunch of the blog articles, a bunch of the recommendations that are out there that people have written about how to tune your database, things that they recommend actually turn out to be incorrect. Using one example would be in MySQL, there's a feature called the adaptive hash index. It basically recognizes that if you have a B plus tree, that you could build an in-memory hash table for you to make keys go faster. By default, it's on in MySQL, and most of the blogs out there say to leave it on. We found workloads where it's clearly it's a 30% reduction in performance if you use that feature. That's a good example of like what the default is and what people recommend you do is actually not always what you want to do. And it varies per workload. And how do you know whether your workload is one of the ones that shouldn't be using it? you'd have to find out manually or use something like OtterTune to figure it out for you. That's probably been the most surprising thing. I can't think of anything. I mean, the database developers at these major systems, they're also in the database business too. So like they want to be very conservative as well. So they're not going to like do something that would be super bizarre. Like turning off disk writes is probably the most aggressive optimization they could probably expose to you. And in some cases, that's actually the right thing to do. It'll make things go faster, but it's probably what most people probably don't want.
And in terms of actually being able to work with OtterTune and determine what are the priorities for optimization that I'm working on, I'm wondering what the actual user experience is of saying either I want to optimize for latency or I want to optimize for speed, or to your point of increasing the number of disk writes, I want to optimize for the durability and safety of my data, at the expense of things like latency or speed.
So again, for durability and safety of data, like that's the default OtterTune. You can override it and say, turn off fsync for log writes, but we don't expose that to the user now in the interface because again, it's like we don't want people shooting themselves in the foot and causing problems. So the way it basically works is you set up the credentials, allow OtterTune to connect to the database. You specify whether you want OtterTune to monitor the database or actually tune the database. And if you're just monitoring, then we're just collecting the metrics and using that to build our models and understand your workload a bit more. If it's tuning, then you specify whether you want to restart or not. And again, we don't want to restart when you're running in production and it causes problems. So we have to ask you whether you want to restart or not. And then based on that selection, we then expose a list of recommended knobs that you'd want to tune, that you could potentially tune, and then along with some default ranges of what values that you could potentially set them to. And then that's it. That's all you really need to specify, other than, again, do I want to optimize for throughput or latency. Cost is a weird one. It requires you to move to a different instance type, at least on AWS. That's downtime, and that's something we don't want to do. So it's typically you want to maximize throughput, maximize cost. Improve throughput and throughput cost. And then that's enough to figure out, I'm getting better performance. We're not there yet, but we think our models can then be used to suggest to the user that this is what you're getting now on this instance size and this provision IOPS on Amazon. But if you downgrade or upgrade and let OtterTune manage things, then this is the performance you'll get, and you'll pay this more, this amount less. So we've done our own experiments with RDS where we can get the same performance on one instance type on a machine that costs half as much, right? If you're using the Amazon as the default config. So we can show that we can get you half the cost points. But that's not something that can get you you can pay half the amount and get same performance. But that's not something we want to do automatically because, again, that transition, that movement is downtime, and we don't let OtterTune do that.
For the case where you say, I don't want you to automatically apply the changes, I just want you to show me these are the parameters to set. I'm curious if you have the ability to kind of priority rank them of, these are the ones that don't require you to restart. This is the expected sort of range of performance improvement that we think you're going to get. Or if you have any capabilities or plans to offer anything like that in the user experience.
We don't have that yet. That's something that we could add. There is an internal algorithm that ranks the impact of knobs. So one of the things we do is we run a lasso regression to estimate what knobs will have the most impact on performance. And that's how we determine, here's the top 10 recommended knobs you should start with tuning with. You can span that over time. So we could do something like that that you're suggesting, that take the expected gain from the machine learning algorithms and expose that to the human. Hey, if you let us tune this for these knobs, you'll get this percentage improvement. If you tune these other knobs, we'll get this kind of percentage improvement. And of course, there has to be a confidence interval to this, because if the model hasn't converged yet, the accuracy of the recommendation you're making can vary a lot. But humans also have a hard time reasoning about these things. So that's why we haven't maybe done that just yet. But that's something we could consider.
Another thing that you touched on earlier is the fact that there are some systems that offer some automated tuning capabilities that might be built into the database or that run inside the engine, but that they're inherently limited by the fact that they have a very sort of small view of the world where they only have experience of that one database and they're not able to learn and train across a variety of different workloads. And I'm wondering what you have seen as some of the compound benefits of being able to run OtterTune as a centralized service and be able to work with and learn from a large variety of database instances with variability across their workloads.
So being able to reuse training data across different databases, it allows you to generate the better configuration or more optimal configuration more quickly. It basically means there's less learning time. Again, this assumes that the application workload you're trying to tune on a particular database is something that we've seen in the past. And if you come out of left field with something we've never seen before, we have no prior knowledge of anything that looks like this, it's just going to take the same amount of time. You have to learn from scratch in that regard. But most workloads are, if you had to see something that's dramatically different, it reduces the convergence time of the model, how long it takes before it produces a configuration recommendation that it thinks is confident that it's going to do well on. So that's sort of the main benefit. And where this matters is in really large fleets, like if you have hundreds or thousands of databases, again, no human could go and tune each one individually, but maybe you also don't want to go through the full process of like setting up a clone, capturing the workload trays, spare hardware, and doing all that sidecar training that we talked about before. You could potentially run directly on the production database with minimal downtime and allow you to tune it more quickly. That's where we think one of the big benefits we're going to see with OtterTune is in that environment where you have just this large fleet, most of the workloads mostly the same, but maybe just a little bit different, but you can still tune them exactly in a way that you couldn't do if a human was doing it or if you were just using a rule-based tool. So I think reducing the amount of time it takes and potentially the number of research you have to tune a database is the big benefit you have from reusing training data.
As you've been working on doing the research for OtterTune and turning it into a product and working with customers and adding compatibility with different database engines, I'm wondering what are some of the most interesting or unexpected or challenging lessons that you've learned in the whole process?
This is not exciting, but lawyers take a long time. Because, when I was at the university, any kind of legal arrangement we would have was handled by the university lawyers, and everybody wants to hang out with people from Carnegie Mellon, so the terms are very favorable what we can do the research. Now you're a startup, and it just makes everything just more challenging. Things I didn't have to worry about as a professor or as a researcher at the university, now have to worry about, like liability insurance and all those things. That's been the thing that's been most surprising, just how much longer things take when you try to do stuff your own, again, from a legal perspective. But the problems are the same, right? The problems don't go away. Everybody is struggling to manage these databases. And so we think we're solving an important problem. It doesn't solve all the problems with OtterTune, but we think this is an important problem that has not really been addressed in this sort of this meaningful way that we're trying to achieve.
OtterTune is definitely a very impressive system, and it offers a lot of potential upside for people who are using it. But what are the cases where it's the wrong choice and you would be better served either by tuning things manually or by running with the defaults or maybe using a different database engine entirely?
You almost never want to use the defaults. I'll just throw that out right now. Certainly don't use the default configuration you get from the OS package maintainers. Like if you call apt-get install MySQL, they assume you're running on a machine that has 160 megabytes of RAM. Like, it's not realistic. So the defaults always be bad. The Amazon default is better, but it's never going to be optimal. The tuning tools like PGTune or the MySQL tuner, various ones from the commercial vendors, they're better, but it's still going to be not as optimal as what you can achieve with either a very expensive human expert coming and doing this or something like OtterTune that can automate it. So the default's always bad. There's other issues you have to deal with managing a database system. So physical design is another big issue, like picking indexes, picking sharding keys. That problem doesn't go away with OtterTune. OtterTune can come up with the best configuration that you could possibly have for your database, but if you have no indexes and all your queries are doing complete sequential scans on a billion rows, there's nothing we can do to make that better. So physical design still matters. There are some open source tools and some commercial tools that can help you pick indexes. That's something that OtterTune doesn't address right now. Whether or not you should switch to a different database system or to a different storage engine, that's also outside of the purview of what OtterTune is trying to solve, at least for now. Because again, that actually requires access to the database, it requires access to the queries, understand how you're using the database. And that's not something that we want to touch right now because, again, of all the privacy concerns, like people are paranoid about data leaks. And so right now, OtterTune doesn't want access to these things. We only need the metrics. We only need the configuration. So we avoid these problems. But that means we can't solve the problems like picking indexes or telling you what database systems to switch. Switching database systems, too, is also not something that you could easily automate as well because the dialects, SQL dialects are always going to be different. There's other aspects like the ecosystem, how it's hooked into whatever the build environment, the CI environment you have. So that's not something that you'd want to automate very, at all right now either. there's a bunch of humans that need to be involved in that decision. So I think knob tuning can still get you a pretty significant benefit improvement, without having to make drastic changes like changing to a different database vendor.
And as you continue to work on OtterTune and work with customers and add new engines to it, I'm curious, what are some of the things that you have planned for the near to medium term or interesting areas of research that you're excited to dig into?
Well, so the OtterTune research project is dead. My PhD student, Dana Van Aken, PhD, defended this year, and she's now the CTO and co-founder with me at OtterTune. For a research perspective, like black box optimization at the Carnegie Mellon Database Group, we're not pursuing that any further. So now on the startup side, I think I mentioned we're adding support for Aurora. It's basically going to be very customer driven, so what people are going to be asking for, we'll start adding. There's some other things we have in the works that we're not ready to talk about yet, because as a scientist, I want to make sure that we have results, we can prove that things actually work. So we have some additional things in the work that we can use based on the same models and the same kind of high-level ideas of what OtterTune could achieve, but it's sort of packaging up or presenting them in a different way or doing different things. So we have a bunch of things in the works in that regard that we hope to announce later this year. Now, in the university, on the research side, we have a paper in Sigma this year that solves the second problem of a self-driving database system to do behavior modeling. So the term self-driving for a database is not just a marketing term. Take heavy inspiration from self-driving cars, which partly were invented here at Carnegie Mellon. And we're using their basic high-level designs of how we want to build our self-driving database system. So the three problems you need to tackle are the forecasting, predicting what the queries are going to look like in the future, the behavior modeling to predict how the system will change or the performance will change as you tweak different aspects of it, and then the third piece is the planning phase of deciding what actions to apply, what changes to make going forward based on the forecast. So self-driving cars at a high level work the same way. You do forecasting down the road to predict where cars will be or where objects will be around you in the future. Then you have models that can predict how the car will behave as you turn the steering wheel left and right, or accelerate or decelerate. And then there's the planning portion where you say, what actions do I need to apply to get me to my destination? What we're trying to build is working the same way. So we have the forecasting piece. We now have the behavior modeling piece in Sigma this year. And then we're working on the last one to do the planning components. So there's a bunch of work in this space where we're trying to get better observation of the runtime behavior of the database system to feed that into our models. We're looking how to reuse replicas or sort of solve that problem of cloning the database and capturing workload trace. Can we do that entirely online using high availability replicas without having to provision additional machines? So there's a bunch of these kind of problems we're looking at. We think we almost have the circle complete where we can do planning, apply actions, and observe whether they help us. But there's still a lot of things to do on the problem.
Are there any other aspects of the work that you're doing on OtterTune or the overall space of database performance automation that we didn't discuss yet that you'd like to cover before we close out the show?
I think that observability is going to be a big issue. And I think, as I mentioned, and it's going to have two aspects. It's going to be, one, observing metrics and data that you can then feed into machine learning models to control things. But then at the end of the day, you're also going to need to have human decipherable or human understandable explanations of why the algorithms are making certain changes. Sort of like people that are really interested in machine learning and people who are working in this space, they're like, oh yeah, sure, we should totally automate everything. We can do this. But it's the people that actually deploying the databases that actually make sure things are running smoothly. They are going to be rightfully hesitant to turn controls over entirely to machine learning algorithms. So I think that we're going to need capabilities to assuage their fears and tell them why the database or why the machine learning algorithms are making changes to the database a certain way. So that's something we potentially want to add in OtterTune to say why we think these are the right knob configurations because your workload looks like a certain way. And then certainly on the noise-based side, it's sort of the same problem, but now it's even more complicated because now it includes forecasting and behavior models and a whole bunch of other components in the decision-making process, where OtterTune sort of has a more straightforward, a single model approach. So I think that observability and explanations for humans of why things are occurring is going to be a tough problem. And that's a whole nother research area in machine learning AI right now as well.
Well, for anybody who wants to get in touch with you and follow along with the work that you're doing or try out OtterTune, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
So that's a pretty big question to end with. My current thesis that I'm sort of playing around in my head is I think we're in the golden age of databases, meaning that there's so many choices, there's so many open source projects, there's so many commercial products, there's so many things out there, and it's really a fascinating time. And unlike in the 1990s where there was only a small number of databases and maybe some things built in academia, but everyone's sort of trying to be very general purpose and solve everyone's problems. We're in this really nice era where there's these niche databases that are solving specific problems or specific workload challenges that we design the system based on just that environment, just that workload. I think that's really fascinating. And of course, now the problem is with so many choices, how does somebody actually navigate this environment or navigate what are the possibilities out there? That's a hard one to solve as well. But I think something like that would sort of guide people to say, okay, your workload looks like this, your environment looks like this, your queries look like this, your data looks like this. Here's what you should be doing. I think that would make a lot of people's lives easier. I don't know what that is, and I don't know how, is it just a decision tree? Is it a flowchart? Is it a website? Or is it something automated that can decipher something? It's tough to say.
Yeah, it's definitely an interesting problem statement. As you said, it's not easy to envision how that would manifest because it could be a decision tree, but then what if your assumptions about your workload are wrong? Or maybe it's something that lives in your database that says, you're using a relational engine, you should be using a key value store or a document store for these access patterns. And, now you have to go and re-architect your entire data model.
Database systems don't die, right? Companies go under, sure, and then sometimes the products will fold, but there's a surprising number of people that are running on legacy systems that have been long. The companies have been shuttered. The company has been sold off to a holding company, and there's milking the maintenance fees. Once you make that choice of I'm going to use database system X, it's very, very hard to get off that. And so that's a really hard decision for a lot of people. And helping them say, hey, this is what you should be doing before they make that big plunge, I think would be well received.
Absolutely. Yeah, and definitely a lot of avenues where that would be useful, including for people who are deciding which data warehouse am I going to use.
Yeah. I will say Postgres is so good, right? It's gotten, in the last 10 years, the development has accelerated. It's a phenomenal data system. And to be honest, 90% of the people out there, Postgres probably is the right choice for most things.
We'll just make a website, which database should I use? And it just says Postgres.
Yes. I think actually that might exist.
Probably.
Yeah.
All right. Well, thank you very much for taking the time today to join me and share the work that you're doing on OtterTune. It's a fascinating system and one that I definitely plan to at least test out for my own use cases. So I appreciate all of the time and energy you've put into the research and commercialization of that. Definitely look forward to seeing what else you put out. So thank you for all of your efforts in this space, and I hope you enjoy the rest of your day.
All right, thank you so much. Take care.
Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.